This video clip is a brief introduction to quantum theory. A more detailed explanation can be found by downloading the ebook Quantum Theory, a Concise Guide for Beginners, which can be obtained from lulu.com. This is the iconic Bohr-Rutherford model of the atom. Unfortunately, it suffers from two major flaws. One concerns the confinement of the protons within the nucleus, and this is dealt with my other video clip on high energy particle physics. The one we will be concerned with here is the instability of the electrons in orbit around the atom, since Maxwell's laws states that such accelerating electrons should continually emit radiation and therefore spiral into the nucleus. So this paradox is resolved by modern quantum theory, as we shall see. Classical physics relied upon two major pillars. One was the particle model of physics, and the other was the wave model. And most physics of the end of the 19th century could be dealt with one or both of these models. However, there is a conflict between these, which was brought about by the study of black body radiation. On the left there we see the Rayleigh-Jeans theory, which is predicted by bringing together the particle model by considering vibration of the molecules in a heated perfect black body, and trying to reconcile this with the wave model of the radiation emitted. It predicts that the graph should rise steeply at the short wavelength, hence the ultraviolet catastrophe name to it. What is observed, however, is shown on the left with those distorted bell-shaped curves. By making a rather simple adjustment to the equations, by insisting that energy of the vibration is discrete, i.e. energy equals h times the frequency of the radiation, where h is a constant introduced by Planck, the curve is made to fit perfectly with that experience in experiment. This idea of discrete energy was taken up by Einstein to explain a completely different effect, that of photoelectrons being emitted when light of a certain frequency is shone upon certain types of materials. If the frequency is too low, no electrons are emitted, no matter how intense the light. However, once the frequency reaches a threshold amount, then electrons are emitted. Again, this can only be explained by considering the fact that the light itself now can only exist in discrete packets or photons. This is a brief potted history of how the notion of what light consisted of has oscillated throughout the ages. This wave-particle duality is encompassed by modern quantum theory, which will be explained through the remainder of these slides. Also note that de Broglie proposed that particles such as an electron can likewise behave as waves. And it's this duality between waves and particles is the essence of modern quantum theory. There is a brief derivation of de Broglie's proposal that wavelength is equal to Planck's constant, h divided by momentum. This is why electron microscopes can resolve much smaller detail than optical microscopes. Because the momentum is large, the wavelength is much smaller. There is another derivation of this and indicating how it relates to Heisenberg uncertainty principle. Since the more resolution we require on the position of a particle, the smaller the wavelength needed. However, this corresponds to quanta of very large momentum, and therefore the interaction would cause a disturbance in what it is we're trying to measure. So although we increase our precision of position, we produce more uncertainty relating to how the particle will subsequently move or its momentum. It can also be re-expressed as an uncertainty of energy times the time period over which it is measured cannot be equal to or less than Planck's constant. And there is a little more detail relating to that. So applying Heisenberg uncertainty principle, we also arrive at the understanding that even a vacuum can contain fluctuating particles. They can borrow a certain amount of energy, and providing it is paid back within a very short time period, it doesn't violate Heisenberg uncertainty principle. And this is the basis of what is known as the quantum field theory. So we see that even the story of our understanding of the vacuum has altered over the ages. So Heisenberg uncertainty principle allows the borrowing of energy, and Einstein's E equals mc squared allows the creation of particle-antiparticle from this energy, providing it is returned to the energy is returned to the vacuum within a small enough time period. There is some experimental evidence of this wave-particle duality, not just for light but also for particles such as electrons or any other subatomic particle. This is just a brief list to indicate the wide variety of applications of quantum theory. Its very nature means that it pervades all physical phenomena, at least at the very small microscopic level. It can be applied to low temperature physics, cryogenetics, or even the interior of stars, as well as modern state electronics here on Earth. Although Einstein won the Nobel Prize for his photoelectric effect, he was one of the biggest critics of modern interpretation of quantum theory, what is known as the Copenhagen interpretation. And a very famous debate took place throughout the decades of its development in the last century. Bohr's interpretation, the Copenhagen interpretation, is the one that's generally accepted these days. The simplistic notion of quantum theory can be depicted as shown, in which electrons occupy discrete energy levels, and the transition of an electron to a lower state, should a space become available, leads to the emission of a photon. Pauli's exclusion principle prevents any two electrons from occupying the same quantum state. So if the energy levels are full, there is no availability for an electron to undergo this transition. This shows more detail of those notions in relation to not only the principal energy levels but also the subshells. Note, however, that it still holds on to the notion of well-defined orbitals of the electrons as shown towards the bottom. So this is only something of a halfway house. It's old quantum theory and is not the modern acceptable version. So let's now take a look at this. It is Schrödinger's equation which describes the atom, and it leads to the notion of probability orbitals rather than exact classical orbits. So what's indicated there are probability clouds of where the electron could be for different energy levels, and this results really as a consequence of Heisenberg uncertainty principle. But as mentioned, no two electrons can occupy the same quantum state as incorporated in Pauli's exclusion principle. And there is a brief summary. Here are some interesting examples of outcomes of this theory. More details can be found on websites. And finally, a reminder that a more detailed explanation of this and other topics in physics can be found at the web link shown.